Hello everyone, this is Dr. Hopkins recording the next video in our series. In this video we're going to talk about phase diagrams. So we're still in the discussion about phase changes. Okay, so phase equilibrium. Basically a phase diagram is a pressure versus temperature plot. So if you remember in the last video we were dealing with chemical potential versus temperature and looking at those plots. Now, chemical potential is not something that we have an easy measurement for. I mean, I can measure the pressure using a barometer pretty easily. Measuring the chemical potential requires understanding how a reaction is changing and so forth. So this is something where we have one measurable and a second measurable, temperature and pressure, very easy. Okay, anyway, so we're going to consider basically a two-component system. So we had a two-component system, alpha and beta, where those are the two phases, okay, in our phase diagram. So we've already established that they're at equilibrium when the chemical potentials are the same. So if we perturb pressure or temperature, we're going to change that equilibrium. Okay, so that would mean we'd have a change in the chemical potential of alpha and beta. And we can represent those here because these are just free energies, and so they're related to the entropy and the molar volume. And so once a new equilibrium is established, so you change pressure and temperature, you stop changing it, a new equilibrium gets established. At that point, the change in alpha and beta are the same, so we can relate these two equations the same, which allows us to rearrange and get what's called the Clapeyron equation, which we're going to use quite a bit in the next few days. So the Clapeyron equation looks at how pressure changes with temperature. So if you think about it, it's a pressure versus temperature plot. This gives you the slope. Okay, so we have the difference in the molar entropies of the two phases and the difference in the molar volumes of the two phases, so delta S and delta V. So let's look at how this would implement itself in an actual phase diagram, or in actual phase changes, I should say. So the Clapeyron equation gives us our slope in our phase diagram. So we have reiterated the Clapeyron equation from the last time. So if we think about what are the phase changes, the common phase changes, there's one that I'm not showing, which would be solid-solid. And solid-solid phase changes are a little bit more complicated to deal with in terms of their changes. But let's just deal with the three fundamental phase changes. So if we have liquid to vapor or liquid to gas, so we essentially boiling, vaporization. So we're going to set liquid as our alpha phase and vapor as our beta phase. If we go back to the previous slide, so that sets that our molar entropy as we go to vapor, third law tells us that the entropy increases as we're going up, so that our molar entropy is greater than zero, right? So that's a positive value. And then what about the molar volume? Well, is the molar volume of vapor or liquid larger? Clearly the vapor expands to fill the volume of the container, so that's also greater than zero, so our vapor is bigger than our liquid. So both of these are greater than zero. That means our slope is greater than zero. Okay. We do the same thing for solid to vapor. As you can imagine, the same trends hold. We have greater than zero. So along the sublimation, along the vaporization equilibrium line, those slopes are always positive for all substances. Now, the one that's a little tricky is the solid to liquid phase diagram. So if we're looking at that now, once again, by third law, we know the entropy increases as we go from solid to liquid. We have more mobility. If we just think of from a disorder standpoint, we have more mobility. So the entropy is going to go up. So that part is going to be positive. But what about the molar volume? Well, in most of the time, the molar volume for most substances, the molar volume of the liquid will be greater than the solid. So if you want to think about it, the density of the liquid is less than the density of the solid. In that case, you would have a positive slope. But there is one very ubiquitous exception, and that's water, right? Where we have the density of solid is less than the density of liquid water, right? Ice floats. So then your molar volume will be less than zero. Your slope would be negative. Okay, so let's look at a phase diagram and look how this shows itself. So a phase diagram, and here I have my kind of sketch. it's pressure versus temperature. We have if we're in these pressure and temperature, we're solid. These pressures and temperatures, it's pure liquid. And these low pressures, higher temperatures, it's gas. You'll notice, so the solid gas, so these lines represent, if you're on that line in terms of a pressure and temperature, two phases in equilibrium. Okay. Now you'll notice the slope is positive. And then the slope between liquid and gas is positive. That's for all materials. And in this case, I show one where the slope between solid and liquid, so the equilibrium between these two, is also positive. That's most materials. So here is one where the density of the solid is greater than the density of the liquid. Now, one thing you also can get is you can get triple points. Okay, a triple point is where you have three phases in equilibrium. Since I'm just showing solid, liquid, and gas, at that particular pressure and temperature, we have all three in equilibrium. We change the temperature pressure in any small amount, and we're automatically going to reduce the number of phases. So if we looked at a phase diagram for something like water, where the density of the solid is smaller than the density of liquid, I've not drawn it very well, but you'll notice we have a negative slope. And actually what we'll do is we'll look at the quite complicated phase diagram of water in class, especially with respect to the solid phase, which is not just one phase. So until next time.